Hi, I'm Maureen Rhemann, but you can call me Mo. Everybody else does. I got a lot of criticism from using transdisciplinary, but I put it in enough papers that people are now really picking it up. We have a world where we have colliding trends. We've got, particularly in technology, because we have a world that continues to flatten and we have information dissemination everywhere. So we've got chips that are 60 to 70x faster. Those are going to be neuromorphic. They're going to be, which are much like brain on a chip. In many cases, you have to grow them. And we're going to have quantum computing, neuromorphic computing, which again makes another leap of faster speeds. So that again takes our networks to be 60 or 70x faster. Then we're going to have networks themselves that are faster through 5G, through processing data at the edge of the network. And now our fourth trend is neuroscience, which is really the glue that knits everything together. So neuroscience and biological sciences are now our emulation that we use for computational dynamics and networks. They're the glue that really holds things together. Everything becomes about neuromorphics, about neuroscience and cellular biology as we try to transfer those things into ways that people can use them. The only way to really do that is to transfer it into code, to transfer it into technology, and then we've got a language where we can communicate with people. But now, the body, our cellular structure, and our brains and our mitochondria, that is the language. The computational brain is the language of where we're going for everything. And so back to your question, transdisciplinary, we get that from multiple fields. In a world where data is connected and where information is connected, we can't just take something from one field. We've got a network of multi-connected trends and multi-connected fields that we need. And every piece of that tells us something that can help us predict the future. So if we look at a cell that can emulate itself, cell biology can tell us what the next cell is going to be like. But we can use other disciplines like art. We can look at beautiful things like origami, or we could look at art from an artist from the past. We can look at planetary science. We can look at physics, mathematics, fractals, and other disciplines that we can use in order to figure out what the future will look like and in order to predict. So my passion is prediction and being able to understand what people are thinking, what they're going to do in the future, how we can help people with science. And the world is actually a very perfect world. If we look at biology, we look at the beauty of flowers, we look at the beauty of nature, the beauty of planets, zebras, snowflakes. One of my favorite things to think about are snowflakes. They're perfect. They're geometry, they're biology in their own way. And if we look at a superconnected world, we need those disciplines. For example, I created something called 7S ADP as a prediction methodology, and it utilizes fractals, futures, physics, and neuroscience in order to think about the future and think about future scenarios, because we're looking at disruption in a way that we can look at asymmetry preceding disruption. So transdisciplinary means we need to go grab things from other fields. We need to connect other fields. We need to understand them in order to create a better prediction, asymmetry, disruption, and computational model. By 2025, we will have roughly 250 zettabytes of data coming in every day on the Earth. That's an incredible amount of data to process. So when people start talking about big data, they're talking about trying to understand and ask questions of data. That's difficult and will continue to be difficult because we have trends that are happening. We have the biggest change in telecom in 25 years. We've got 5G coming online, and we are, instead of bringing in data at the inter-exchange carrier level, the IXP and the POP, we're going to take that data instead and process it at the edge of the network. That's a huge change. That means that you can take data and 5G and your data center, and it moves, fundamentally changing your infrastructure. So that much data changes the paradigm entirely. What we need instead is to figure out what are our questions. Instead of looking at lots of data and looking at patterns, that's great, but we need to say, what is your question? And look at heuristics and draw from other disciplines in order to use our data more efficiently. We also need to think about other disciplines we can use to collect data, and we also need to think about how to characterize data so that it can be in an algorithmic format that can tell us what we need. Bottom line, the last decade's data science is giving way to precision science. And now we need to move toward precision science and precision algorithms. And that changes how we process. It means we need to be better practitioners. I also spent time at Northrop Grumman, McKinsey, and I think every experience we have, our brain processes data with semantic memory, which are facts that we know, and episodic memory are like movies of our life, movies of things we've experienced. In taking those two things together, we're all a product of our experiences and where we go. And when we create a new experience, we try to put things together. For me, I looked at how do you help other people, and how can we use these experiences to make a difference. So the MBA is always helpful from the standpoint that we need to understand demographics. We need to understand and connect science with people's needs, and we need to be efficient about how we do so. The PhD side was an evolution. I've been working on characterizing prediction for a very long time and drawing upon data and using it as an efficient way to predict. The PhD for me, was really simply taking what I've been doing for a number of years, adding new research to it, and doing it in a format that was academically efficient. What it's done since my PhD has been far more fun. I've done more research outside my PhD than I ever did. I had no idea that I would hit my head on a rock somewhere and all of a sudden would be curious about everything in life. I love complexity theories. I love complexity because you could go from snowflakes, you could go from looking at how flowers bloom to the fact that a mother deer has 3 babies or 4 when it's going to be a hard season, and that's predictive. In looking at snowflakes, in looking at zebras, that life is so perfect, the planets hang in the balance, that everything is a system of systems. If we can look at those systems of systems, and even our own cells, we can find prediction. And so over the time that I've worked in prediction, it's been interesting to find all of these other incredible fields that are worthy of utilizing in prediction. I think it's not just data itself, although I will say data is incredibly valuable, and we don't always understand the value of data that we have until we walk back several decades. My company was doing some work with NASA, and we told them not to outsource their weather data because we could go back and look at, nobody's heard this term for a while, they had data that was in ASCII format that had weather patterns from probably 40 years ago. That data we find out now is incredibly valuable. So that said, the new format for that is data that we understand from the human brain. Everything we do generates data. If we could look at molecules in this room, we would be generating data. So we're finding new way to pick up that data, new ways to use that data, and new ways to use it to heal people and to help people. The imprints that we can receive, whether it's from anything giving off energy anywhere, will be invaluable models for the future, and they will also probably help us heal people, and heal people in ways that we hadn't thought about before, in terms of not just using signaling and reaching people with brain signals, like signals that are varied with spectrum, hertz, etc., whether that be music or whatever venue that the brain can process. But we're also going to go into a world where we know more about our sensory systems and how we process, like our olfactory systems, whether we can precision use data such as scent. And that's being done to some extent. So is food, so are other things. But I see a world in the future where we take that down to a precision. What is the algorithm? How many peptides do we need? How many sensory perceptive systems can we use? And can we create a precision formula for healing people? That's where brain science is going, and that's where medical science is going. And back to transdisciplinary, we need to combine them. We need to combine fields. I think we are entering a world that's going to be very different. We have a world flattening, and we have the radical, exponential technological collision that's happening right now. And that means that we need to be teaching tiny little children science. We need to get our children to understand how to code at a young age. Our ways of translating science and knowledge are going to be different, and they're going to be moving at an exponential rate. So as much as it can be people switching fields or doing a PhD, what's more important is that they expand their thinking and their abilities. It's not simply the PhD itself or any of those things. That is nothing more than a piece of paper that tends to portray some form of knowledge. The world, as we know it, will probably experience a time where we'll see maybe 20% of the jobs that we know today disappear. Part of that is we have computational efficiencies. As we move into a world where everybody is closer, where we use technology, more and more links will be taken out. That means more jobs will leave. Where we once had something like Microsoft Word or PowerPoint to portray, the next piece of that is that everybody needs to code. It used to be everybody needs to know PowerPoint. The generations before that is everybody needs to know to type. Now it's everybody needs to understand coding, engineering. Without it, we could face a society that is really a two-class society. People that are able to do things and have knowledge, and those that don't. And which category do you want to be in? It's also a time when anybody can go become more technologically proficient. That includes older people. That includes anyone. So it's not simply a PhD or a degree. It's a function of acquisition of knowledge. We're in an age of an enormous need for continued acquisition of knowledge to compete, to keep jobs, and to be efficient and even conversant in society. I think that you can increase brain efficiency. I also think that you can increase body efficiency by increasing human growth hormone in your body, and you can do that in a number of ways. You can do it by modifying your diet, and the increase in human growth hormone in your body can be done with melatonin. It can be done with probably 11 or 12 different things, but you can also use food as brain food to modify the body, and that could include going on a very low carb diet. So experiments with cooking have been creating desserts that are keto desserts or desserts that have no sugar. I personally believe processed sugar is the devil, that it destroys the mitochondria and we don't want it in the cell. It's very harmful for viruses, in my opinion, or anything else. And there has been recent research that has come out to say that keto diets are very effective in potentially preventing COVID or other viruses. I love making desserts. I love making cookies. I love trying things, fudge, anything that will give somebody a smile. But I think we can effectively create desserts and get rid of processed sugar. We can also do things that stimulate the brain. So if you look at things like almond flour that is providing energy, whether we know that or not, hits workouts and the ability to speed up your metabolism are also very good for oxygenating your brain and preventing deterioration and other things that happen later on. So The first part of the question I would answer as making it usable to people and more real to people and simple in people's lives. And brain science, I'm backing into the second part of the question. Brain science is part of our lives already. And we're finding that it's in everything we do. We're finding that it's going to be the brains of the next generation computing systems. It already is. It's going to be the brains in our future satellite systems. It's going to be the thing that helps us excel cognitively. When we start looking at brain chips, we start looking at cognitive enhancement, but also not what we can do necessarily with putting chips in our brains. It's also what we could do with food, what we could do with between the gut-brain relationship. So in what HBSF can do is to make that usable in people's lives, to make it an everyday, every person experience in all we're doing. When we're doing our workouts, when we're eating, when we're drinking, when we're talking with friends, or when we're recalling our vacations. Maybe we could have better vacations if we, for example, thinking about the studies that have been done in memory and thinking about the future. Right? If you have a vacation and you do the same thing every day, it's one memory stacked within your file system vertically. We would change perhaps what types of experiences we would have. A lot of my work has been thinking about predicting the future, predicting future events, but that comes back to how we perceive neuroscience and how we use perception in our daily lives. So we would change perhaps what types of experiences we would have and how we stack our daily lives. I mean, stopping and smelling the flowers, we want to do that. We want to enhance our experiences of life. So I could see HBSF going further in trying to make science real and having fun with it, enjoying music. We can do cognitive enhancement with music. We can do cognitive enhancement with sports, with just changing our metabolism, with doing HIIT workouts. But we can go way beyond that. In the future, we can do it to a precision level.